Hello, everyone, and thanks for tuning in this afternoon. My name is Nicholas Rubin, and I'm a research scientist on the algorithm and application team here at Google Quantum AI. My primary role is to develop and explore quantum computation for physical simulation. Today, I'll be talking about one of my favorite areas of simulation, chemistry computation, and exploring where to find quantum computational advantage in real-world applications. The focus of this talk will not be motivating quantum advantage from a complexity theoretic framework, but providing numerical simulation evidence of a quantum advantage boundary for chemical simulation challenges that one encounters in industry. So I'll do this by comparing the simulation resources required of modern high accuracy classical quantum chemistry to estimates of quantum resources for the devices we are planning to build here at Google. So the algorithms team spends a lot of time thinking about how we can best simulate systems, other quantum systems with quantum computers. This was the original motivation for building a quantum computer, and it's still believed to be one of the most promising applications. I like to show these popular science article titles as my tongue-in-cheek way of motivating the importance of chemical simulation with quantum computers. Chemical simulation is hailed as the killer app of quantum computers, yielding insight into next-generation batteries or drugs, and has the potential to remake chemistry. While these are attention-grabbing titles, it is my job to articulate the substance motivating them and how quantum computers will actually facilitate these advancements. So to focus our task of numerical evidence for simulation advantage in chemistry, I'll focus on algorithms for simulating the ground states of electrons in molecules or materials. So the governing differential operator for electrons in these systems is written here up on the left. It has a kinetic energy term, an external potential term, and an electron-electron interaction term. And like any partial differential equation, one generally chooses a basis to discretize space and then solves the coupled set of equations in some maybe exact way or approximate fashion. All of the algorithms in this talk will focus on simulating the second quantized representation of the continuous Hamiltonian up on the left, which is obtained after selecting an appropriate basis. So a prominent quantum algorithm that performs the same task, simulating ground states, this Hamiltonian, is the phase estimation algorithm. Now, quantum phase estimation isn't a new algorithm. It's been around for a long time and has been applied to molecular simulation before. In the original proposals for quantum phase estimation, there were only asymptotic scalings with non-specific polynomial factors for the relevant parameters. And over time, the community has refined and defined the asymptotic costs of performing phase estimation for molecular systems. In fact, over the last 2 decades, we've seen some incredible progress, costs falling from impractical values, 10th order scaling in system size, to near linear. So given the past decades of improvements and the promise of quantum computers facilitating discoveries in chemical science, I think it's time for an honest assessment of the constant factors and not just big O complexity. So ultimately, what we want to see is how well modern versions of phase estimation stack up to modern classical electronic structure counterparts. So what I've articulated is the classical versus quantum computation competition that we want to hold. So now one might ask, where do you hold this competition? So the field of quantum chemistry has been around for over 50 years. There's been substantial developments of modeling strategies during that time. And as with any modeling task, we trade off model complexity and computational complexity. Effectively, we can choose either to simulate our Hamiltonian exactly, which we know has a high level of model complexity, namely it's the exact simulation, but comes with exponential computational cost. Alternatively, we can truncate our model to, for example, have only mean field interactions, which has a lower computational cost, in this case, cubic. The field of quantum chemistry develops a wide range of methods and different scalings and seeks to understand how to appropriately apply these methods to different chemical systems. So this poses a challenge for defining quantum advantage because given any chemical simulation task, I can generally get an answer, albeit possibly incorrect, with a low scaling algorithm. So how do I define quantum advantage in this case? The solution that we take here is that we search for chemical systems that demand high model complexity, and we quantify that demand with classical simulations. So, for example, a common drug anti-target is actually the cytochrome P450 enzyme. On the left here, I have a cartoon of the catalytic cycle of the active space. The P450 enzyme is responsible for metabolizing about 50% of the marketable drugs that are out there. So you don't want your drug to bind too quickly to this particular molecule. This is an example from our research collaborators at Boehringer. And what I'll demonstrate is the process of figuring out how high a model complexity is demanded by the system. And then we'll assess the classical cost of simulating at that particular model. Another example is shown on the right. It's a material simulation example from our colleagues at BASF, where the goal is to understand the stability of a lithium battery cathode material with a particular metal. Though I won't have time to go into this example, the story is largely the same, that in order to quantify whether a quantum computer will be useful in accelerating material science discovery in that setting, we would need to quantify the necessary model complexity first before considering applying a quantum computer. So zooming into the P450 case, our goal is to understand that entire catalytic cycle. But for brevity, we'll just consider 4 compounds that are related to that cycle. And all of these compounds, if we were to simulate this at a medium coarse grain basis, they cost about 1,000 logical qubits. Now, classically, what we can do to assess what is the necessary model complexity to simulate this particular system, we can start at the bottom, maybe mean field or density functional theory, and then start going up this hierarchy and simulating the same system. So for example, in the middle here, I have some results from a variation of second order perturbation theory. And what I've plotted is the occupation numbers determined from that particular technique. Now, occupation numbers indicate the degree of multi-reference correlation in your model. The degree at which these occupations deviate from mean field can indicate that higher model complexity is needed to describe the electrons of this system. We can plot the energies and occupation numbers from this perturbation theory and see that for 3 of the compounds, they actually look pretty similar to mean field. But one of those compounds, compound 1, actually has 3 open shells for the doublet case, which should, at the mean field level, only have 1. So this would suggest that we should go to a higher level of theory to confirm the electron correlation in our model. Another example is on the right-hand side. This is a metric that is inherent to a particular method. So single reference couple cluster calculations have metrics that indicate when the method is appropriate to apply or when the results are actually unreliable. In this case, I'm plotting the T1 metric. That's not to be confused with the coherence time T1. There are other metrics such as T2 and D2 and things like this. And we apply all of these metrics and we apply this kind of systematic increase in the model complexity that we're simulating these 4 compounds to determine where we should stop. So the most reliable way of confirming model complexity is to actually ascend the theory hierarchy, right? We want to go to the next level and see if there are properties that are staying the same. And we do this in our case by defining a series of active space models for the 4 compounds that we're going to plan to run DMRG at different bond dimensions. Now, DMRG is a variational method that is more accurately accounting for the electron correlation, of course, at the expense of higher computational complexity. If you're familiar with DMRG, you'll know that it works excellent in 1 dimension, but in higher dimensions, it has weak exponential scaling in the bond dimension. So what we did was we simulated at each of these larger and larger active space sizes in terms of more and more qubits representing our problem, and then extrapolated the classical resources necessary to simulate at the largest size. That's 116 qubits in this case. Now, what we determined is that if you're willing to wait a month of computational time and pay considerable memory costs, you can actually simulate that large active space model within DMRG at a modest bond dimension size. So if we're just to plot that data, sets the field for comparison that we actually want to stack up our quantum computer against. What we want to do is see where does a phase estimation algorithm lie on this particular graph, which would suggest if there is a crossover, a quantum computational advantage. So we'll be running our chemistry algorithms on fault-tolerant quantum computers, and there are important timing considerations when estimating runtimes. So what we have in mind for the system that we're building is that it will have millions of physical qubits that are all well below threshold in terms of error rates. And what this means is we have approximately 1,000 physical qubits per logical qubit. And the result, though, is that for some particular operations within error correcting codes, there's actually a huge constant factor slowdown. Namely, some operations are very, very slow. For example, Toffoli gates or T gates require large footprints or large quantum resources to actually execute. So what that means for us is that when we consider comparing the speed of a quantum algorithm executed on computers that we're going to build in 10 years to today's electronic structure to define some type of simulation advantage boundary, we need to take these constant factors into account. So just to give a kind of an idea of how large this gap can be, let's consider a classical NAND gate. This has a space-time volume of about a transistor nanosecond. If we consider the quantum equivalent of the same type of operation, a quantum NAND or distilling a Toffoli gate, this has a space-time volume greater than tens of qubit seconds. And this is generally what people call T-factory. And so this is why it's actually really important to go beyond asymptotic scalings when thinking about defining quantum advantage in physical simulation or even just searching for it. We need to understand how these large computational speed differences affect the underlying rates. So the algorithm that we are actually going to focus on is phase estimation. It allows us to sample in the eigenbasis of a given Hamiltonian, and it works in the following way. So we're given some Hamiltonian, and we consider its eigenvectors and eigenvalues. And we're also given a state, psi, some ansatz, that we're going to say has reasonable support on the ground state. We perform a circuit that corresponds to a unitary that's generated by a simple function of that Hamiltonian H, and that encodes the spectrum. For example, we could actually take that function to be the identity function, and therefore the unitary that's generated by this Hamiltonian could be synthesized approximately through trotterization. Now, if we were to apply our U to an the approximate state expanded in the eigenbasis, we can see that we accumulate a phase proportional to that eigenvalue or spectral information of our Hamiltonian. So those of you who are familiar with quantum computers, you might know that they're very good at learning phase differences. And you might guess where we're going with this. If we were to perform this time evolution, this controlled unitary, we'd be able to read off the phase difference with a number of queries of U proportional to 1 over epsilon. If we want to quantify the cost of quantum resources to leading order, we actually need to quantify the cost of applying or implementing this U and scale that by the appropriate factors. So it's actually important to point out that the cost of this algorithm is scaled by our initial overlap. So you might consider that for a complicated system, getting a high overlap might be pretty challenging. But we can leverage the years of development in classical electronic structure for creating this ansatz psi that we can ask or hope for having a high overlap. Overall, when we talk about quantum resource estimation, we'll be talking specifically about synthesizing each query to U and counting in terms of the number of logical qubits required and the number of Toffoli gates required. We can then translate this into a runtime given the estimates of what we're going to build, given the surface code, and the input physical error rates and the number of T-factories. So the modern versions of phase estimation that we're going to consider for chemistry actually have substantial scaling improvements over a trotterization version that change the function f of h, and thus the unitary that we're phase estimating changes. The function that we actually evolve under is related to the arc cosine of the Hamiltonian divided by a problem-dependent parameter lambda. And it turns out that we can very efficiently synthesize these unitaries generated by this arc cosine function. So applying the same logic before, we need O of lambda over epsilon queries to U, and then to determine the cost of leading order, we need to count specifically how difficult is it to synthesize each of the important unitaries in U. So for sake of time, I'm not going to derive the specifics of qubitization oracles, which give you the unitaries that are generated by arc cosine of this Hamiltonian. Instead, I'm just going to provide you the answer that using a linear combination of unitary representation of the Hamiltonian, the unitary synthesis required to implement this arc cosine primitive or this arc cosine function requires two primitives called select and prepare. So given the Hamiltonian represented as L unitaries, prepare builds some superposition on log L ancilla with amplitudes proportional to the weights in your LCU. And select takes as an input the ancilla register and applies U to the target state register. So where does chemistry come into this? Like, how does this relate to chemistry at all? It turns out that you actually have a lot of freedom in terms of how you express your Hamiltonian as a linear combination of unitaries, and that different selections of unitaries change the total number of ancillas required, the cost of implementing select, and the size of lambda, which recall directly scales the cost of phase estimation. So in terms of chemistry, one way that we actually have freedom to change these linear combinations or change the linear combination of unitaries is to exploit the structure in the problem. And there's been a lot of advancements over in recent years considering structure in the electron-electron interaction term, this 4-mode term. And what we can do to synthesize different unitaries is actually consider different factorizations of this 4 tensor. So there's one particular factorization called singular factorization, which splits our 4 tensor into 2 equivalent 3 tensors. There's double factorization that takes that one step further. And then there's another more recent factorization called tensor hypercontraction that you can imagine this 4 tensor as a small little tensor network and do hypercontraction between 2 or 3 of the edges. All of this leads to different types of linear combination of unitary expansions of the Hamiltonian, which then will lead to different costs. And so that's what we want to compare in terms of comparing to the best classical algorithms. So once we've picked a particular linear combination of unitaries expansion of our Hamiltonian, it's time to synthesize, select, and prepare. And so what I have down here is just really kind of a cartoon. This is an example, select and prepare. They're actually a bit more complicated than this, but it is to indicate that what we do is once we have this linear combination of unitary, we go ahead and just build the circuits and literally count the number of Toffoli gates and ancilla required to synthesize each of these operations. And from there, we can then think about how to compile this into the surface code. So once we have counts for select and prepare, and we know how many times we need to apply each of those operations, we can think of how long it might take a real quantum computer that we're going to build to actually execute all of those. So for this, we need some assumptions about our hardware. And my colleagues on the hardware team have laid out a beautiful roadmap to get to these error-corrected devices. And so we can import that information into our cost models. So we're going to assume that we have a 1 microsecond cycle time in the surface code. We're going to assume something about the physical error rate, and we know the logical qubits and the Toffoli required at each step of phase estimation. And what our code is going to do is optimize the code distance necessary for constant success probability for running this particular algorithm. And so remembering back to what we started with, those 4 particular molecules in those active spaces that we labeled A through G, what we can do is then count the number of logical qubits and Toffoli gates required to phase estimate each of those to a particular error, and then compile those completely all the way down to the surface code runtimes, making the assumptions of the 1 microsecond time, a physical error rate just below threshold, and a number of Toffoli factories. And what we find is that there is substantial difference between the various linear combination unitary factorizations. And the really exciting thing is that we see these asymptotic scaling differences kick in far below what you might expect in terms of what asymptotic scaling actually means. It is nice to see that with the tensor hypercontraction factorization, we can get the largest of these systems just below 100 hours of runtime, which is considered the gold standard of electronic structure calculation, about a week of runtime. And this requires a code distance of 29 in the surface code and merely 4.6 million physical qubits. So something that I think is pretty accessible. So now back to our original goal. Our original goal was to take this scaling estimate runtime from DMRG, and we want to see where the quantum computer stacks up for estimating ground states. So this was the plot from we have before. We have full CI on those, which is exact diagonalization, an exact solution, which we can perform for the small systems. And then after that, we perform modest size bond dimension DMRG calculations and determine that runtime. And that took about a month. And now if we compare a lower number of Toffoli factories just to make this a fair comparison, namely single-threaded calculations, we can see that there is indeed a crossover after taking our resource estimates, compiling them fully into the surface code, and getting out code distance required and runtimes. For in this case, considering fewer Toffoli factories, we would need 5 million qubits and 140 QPU hours of runtime. So this is pretty exciting. We actually have code to do this. So this is up on our open source repo, OpenFermion. So please go ahead and check it out. Any chemist can go in and see how long their molecules will take to simulate. But what I wanted to emphasize before I leave is that quantum simulation advantage in chemistry can be defined in the context of necessary model complexity. So we're not going to be able to just pick a molecule and say, oh, that's something that we should define quantum advantage on. It's very likely that we wouldn't need necessarily a high model complexity to simulate that compound. Modern electronic structure is powerful. It's a moving target. And so we'll have to continuously reassess what this quantum advantage boundary is. And due to the constraints on speeds of quantum computers that we're going to build, gate counting is actually a really important activity if we want to accurately define simulation advantage and find applications of quantum computers. I didn't get to touch on the open questions around fault-tolerant algorithms that we learned in this project. What we were doing was sampling in the eigenbasis of a particular Hamiltonian that was actually relatively small. There's a large amount of electron correlation called dynamic correlation that we might want to be able to include in this system, and that would demand different fault-tolerant algorithms. And so I think there's actually a lot of things to do here to make this a full quantum computational pipeline for chemistry. And so with that, thank you very much. I have some special thanks to the Googlers who helped me with all of this work, and then some of the external authors who participated in this, Josh Goings, who was here and now at IonQ, Dominic Berry at Macquarie, Alec White and Toru Shiozaki at QSimulate, Junho Lee at Columbia, and Matthias and Christopher at Boehringer. And thank you for your attention.